Catalysis. This was also mentioned in that video. We've learned that we can affect the rate of a reaction by altering the concentration of the reactants or by changing the temperature, right? Both of these have their limits. You cannot increase the concentration past, say, the solubility of that substance, right? You can't increase the temperature beyond the decomposition point of the reactants. So those affect the rates, but there are limits. A catalyst increases the rate of a reaction without being consumed. And the way it works is it provides an alternate mechanism where the rate determining step has a lower activation energy. It's just an alternate pathway to get to the same place, but requiring lower energy, and so it's faster. I didn't do this example yesterday, but I'm going to do it here. Okay. I really like analogies. So here we have kindergarten teacher, and here we have the kindergartners. Aren't they cute? I don't know why everybody has their hands in the air. They just don't care. So they're on this field trip at the farm, and they have to get over this fence. Well, these guys are small, the fence is tall, it's going to take them a while to climb over the fence, right? That's a high activation energy. It slows down the process of the whole group, right? Because we have to get over the fence. Well, if the teacher stands here and picks the kids up and lifts them over the fence, it's going to go much faster, right? So the teacher is the catalyst. Makes an alternate way for the reaction to occur. Now, something else the teacher could do, maybe because she grew up on the farm and she realizes that those fences, the rails aren't actually attached because it's that kind of a fence, and so you can just slide it over and drop one end, and now the kids can climb over all by themselves much easier, but the catalyst has provided an alternate pathway. Okay? So that's what a catalyst does. In the decomposition of ozone, which we were just talking about, the uncatalyzed reaction occurs in a single elementary step. You have a reaction between O3 and an oxygen atom. It goes through a transition state, it's high energy, and then it produces the products. That activation energy is high, so the rate is fairly slow, and thus the ozone layer does not just rapidly decompose into oxygen. So this is a good thing. But chlorine atoms can catalyze this reaction. They can make available another pathway that has a lower activation energy. So if chlorine is available, it's a little bit like the teacher helping the kids over the fence. So now we have two transition states, but they are much lower in energy, and so this reaction can go much faster, and the ozone can decompose into oxygen much more quickly. Does that make sense? The catalyst provides a pathway with lower activation energy. So this is a mechanism for the catalytic destruction of ozone by chlorine. Chlorine collides with an ozone molecule and forms this intermediate ClO, and then the ClO runs into an oxygen atom and reforms the chlorine. And so what we have here is we have an intermediate. The intermediate is formed and destroyed. The catalyst is destroyed and reformed, or gets busy with someone and then lets go of them, right? So when you add this together, the intermediates disappear and the catalyst disappears. Okay? The activation energy for the rate limiting step much lower, reaction occurs faster. The chlorine is not consumed. Where do chlorine atoms come from in the atmosphere? Chlorofluorocarbons, man-made chlorofluorocarbons. These are things like freon. So now the air conditioner in your car uses something that does not have chlorofluorocarbons in it, but that used to be the common thing. And then the air conditioner leaks, and that stuff escapes into the atmosphere. It also used to be used as a propellant in aerosol cans. And so, this stuff was coming out all over the place, and we didn't know that it was bad for the ozone layer. So they figured it out, yay chemistry, right? And so then they're like, oh, we got to stop using that stuff, right? So now, we're not adding to that problem. Another example of catalysis is also kind of related to your car, a catalytic converter. So in California, your car has, if it's a gas-powered car, has to have a catalytic converter to reduce the amount of pollutants that come out of it. And so that's a little device under your car that people like to steal because it has a precious metal in it, platinum, rhodium, or palladium. And so the guys that steal these can get money for them. Apparently it's enough to make it worth their while. Now, honestly, I think most criminal activity, if those people would just apply the same amount of effort and diligence to something that's legal, they would do just as well or better, right? I don't understand it, but that's beside the point. So in the catalytic converter, we get exhaust pollutants like they get converted to less harmful products like nitrogen and carbon dioxide. Nitrogen and carbon dioxide are natural components of air, right? Too much carbon dioxide is bad for other reasons, but it is a natural component of our atmosphere, right? We are all breathing out carbon dioxide right now. It is not toxic any more than helium is toxic. If you had too much of it, you would suffocate, but not because that it's poisonous, but because you wouldn't get enough oxygen. So the catalytic converter has a ceramic substrate that has a really high surface area, kind of like you could think of maybe like a sponge. It's got lots of little holes in it, and so the gas can go through and it meets lots of these catalyst atoms, and that catalyzes these reactions. It also catalyzes the complete combustion of fuel fragments, so not all of the fuel is completely combusted into CO2 and water, and so in the catalytic converter that also will happen, and so we reduce the amount of pollution using a catalyst. Any questions? So you can talk about two different types of catalysis, homogeneous or heterogeneous. So homogeneous catalysis, the thing that's reacting and the catalyst are in the same phase. Solid, liquid, gas, aqueous, the same chemical phase, physical phase. So here they're both in the gas phase. Heterogeneous catalysis, here the catalyst is in a different phase. Here it's a solid and the reactants are gases. So this would be like in the catalytic converter, and this would be like the chlorine decomposing the ozone. So, we just talked about how chlorine catalyzes the destruction of ozone, and so you might think, well, that's why we have problems with the ozone layer. Well, it's part of the problem, but there's this weird thing that happens every year. We get this big hole in the ozone layer over Antarctica. It gets depleted in the Antarctic Spring, which is, the opposite of our spring. So it's like right now, coming up. Yes?
Do you know, this is a curious question, but do you know if Fresno does have the depletion, ozone depletion? Like, there is a hole in Fresno?
Does Fresno have a hole?
Yeah.
No. So this hole just shows up over Antarctica. And it's every fall for us in the Northern Hemisphere, which is in the spring down there. And so it forms, and if you just looked at the status of the ozone layer, like in September, you might be really, really worried. Like, oh no, there's this giant hole, we're all going to die, right? but then it goes away. By the next May, it's not there anymore. Weird, huh? Well, it's not the chlorine. The chlorine is evenly distributed throughout the entire atmosphere. So that can be responsible for thinning the ozone layer in general, but it can't be responsible for this hole that comes and goes. So what's happening here is a little bit different. So the chlorine from those chlorofluorocarbons gets bound up with other substances that are present in the atmosphere, such as ClONO2. So it gets bound up, it gets involved with other elements, and so then it can no longer catalyze ozone destruction. But something interesting happens over the South Pole. So we get these polar clouds that have ice particles in them. And the ice particles catalyze the release of chlorine from these compounds that are holding it captive. So the ice particles are a heterogeneous catalyst for this reaction, which releases chlorine from these different compounds. In the Antarctic spring, where there's more sunshine, right, over the South Pole, there's more sunshine, and that sunlight dissociates the chlorine gas into chlorine atoms. And these chlorine atoms destroy the ozone in that area, and so we get this big hole that forms every spring and lasts around 6 to 8 weeks, and then it goes away. And it's from these clouds that are catalyzing the release of chlorine from these compounds. So again, we want to keep chlorine out of the atmosphere as much as we can. And then the reason the hole forms and then goes away is because in the spring is when the southern hemisphere has more sunshine, right? At the poles, in the winter, the sun doesn't come up at all. It's just dark all day long. And in the summer, the sun doesn't set, right? So when there's more sunshine over the South Pole, over the Antarctic, then we get this hole forming. Kind of interesting. Let's talk about a different kind of catalysis, the hydrogenation of double bonds. You've probably heard about hydrogenated vegetable oil, right? What is that? Well, this is what they do. They put hydrogen into it. So there are a lot of different organic compounds that have double bonds. And in the presence of hydrogen gas, the hydrogen can get added to the compound. We call that hydrogenation. And now it's got a single bond instead of a double bond. And so that then is a different compound, has different properties. Well, this is a relatively slow process at normal temperatures. But if you have platinum, palladium, or nickel, the reaction occurs very rapidly. So you can catalyze the formation of these alkanes. The reason the reaction is slow is because we have a large activation energy because of the strength of the hydrogen-hydrogen bond. So the bond here between the two hydrogen atoms is really strong. In order for this reaction to occur, you have to break that bond. Well, the activation energy is lowered when the hydrogen is absorbed onto the surface of a catalyst. So these are the steps that happen in heterogeneous catalysis. I will not ask you for these on an exam. I won't ask you to list them off. Adsorption is where we have our reactants getting stuck onto the metal surface. It's not absorption, because that would be like a solid absorbing a liquid. This is a gas on a solid. And then those particles can move around. They can diffuse on that surface because they have to run into each other to react, right? So they diffuse, they react, and then the products desorb. They leave the surface. where enzymes are like really spectacularly important is in living organisms. So the reactions that are needed for, say, a human to remain alive, most of those are very slow at body temperature. Too slow for life to continue. So our bodies have enzymes, which are biological catalysts. These are usually large protein molecules, and if you're interested in that, study biology or biochemistry. But we'll just give you the overview here. So the reactant molecule, which we call the substrate, will bind to the enzyme. There's an active site, and it binds through intermolecular forces like hydrogen bonding. And when it gets bound into that activation site, or the active site, it lowers the activation energy of the reaction. So here we have an illustration. Here we have our substrate, and it comes in and binds to the enzyme. These active sites are very specific. Oftentimes they will only bind with one kind of molecule. So it fits in here a lot like a key fits into a lock. And it's things like dipole-dipole forces and hydrogen bonds that cause it to want to get in there and stick. When it sticks in here, then the reaction can occur. So an example of this is the digestion of sugar. So here's a sucrose molecule. That's what's in table sugar. And when your body digests it, it needs to break this bond right here. And that breaks this sucrose into glucose and fructose, which then go on and get metabolized further. Well, that does not happen very quickly. You don't look at your sugar bowl and, it's hydrolyzed into fructose and glucose. No, it just doesn't happen very fast at all. So how does your body accomplish this? With an enzyme. So the enzyme for this is called sucrase. And so the sucrose binds into the active site, and when it does, there is strain put on that bond that needs to break. So it's kind of like, tweaking it as it gets in there, and now it's easier to break the bond, so the reaction happens more quickly. So that bond gets broken, then the pieces leave, and another one comes in, and that happens over and over and over and over again. So enzymes give organisms tremendous control over which reactions occur and when they occur. So your body wants something to happen, it can send an enzyme or produce an enzyme in that region of the body which causes that reaction to occur. The enzymes are really specific. They catalyze a single reaction, and they can speed up reactions by as much as a factor of 1 billion. It's mind-boggling, right? Your body can also control the enzymes with inhibitors. So you can basically, throw a wrench into the works. You can block the active site, and then it can't catalyze the reaction anymore. You take the block out, and it goes. So that's another way to control them. Well, if you ingest a substance that inhibits some of your enzymes, that can be extremely toxic, because a single enzyme, lock up a single enzyme molecule, and that can prevent the reaction of billions of substrate molecules. So just a little bit of a substance that blocks a certain enzyme can cause a big, big problem. Yeah.
Are you done?
Not quite. So this is one of the things that is used in pesticides. So they find something that messes with an enzyme that a particular insect has, or that insects in general have, and you spray that around. We don't have that particular enzyme, and so it doesn't have that same effect on us, although, could possibly have other effects. And so it kills the bugs and doesn't kill us. Okay, question?
No, is it about that?
Yes.